Okay, everyone, welcome. All right, today, so the worksheet has 4 problems on it. Most of them are pretty straightforward. I don't think that there's anything too crazy going on here. Problem 1 in particular is actually really straightforward. That being said, I don't want to deprive you of the opportunity to try it. So in usual fashion, right? Actually, maybe let me just remind everyone what is SL2, what are GL2, because it does come up in the book, but I don't think that we've spent too much time playing with it. So I'm just going to remind us what these are, just so that we have it. And I will say ahead of time as well, we don't need SL2 for this to be true. This is just generally true in SLN, right? So recall the GL, I usually write it subscript here, but I guess that's not what we're doing. So GLNR is the collection of n by n matrices, right? Such that A is invertible. Right? And we know that that's equivalent to the determinant being non-zero. And that's important because when we define SLN, that's defined purely in terms of the determinant, right? So we have SLNR is the collection of matrices, and we could just say n by n if we wanted to, but we can be more specific than that. We can say, we're not using subscript, NR, such that the determinant of A is exactly equal to 1, okay? Exactly 1. So it's not allowed to be anything else. And it's not too hard to show that this is a subgroup. That's really straightforward. I think it's been done in the notes already, so we're not going to worry about that. You can assume it's a subgroup. And now this question says, show that SL2R is a normal subgroup of GL2R. Let's not worry about 2, because it turns out that the proof is just as easy if you work in SLN, okay? So show that SLNR is a normal subgroup of G. I keep putting subscripts because that's how I always do it. Gen R, like so. Okay, so I'm going to give you a couple of minutes to do this. Like I said, this one really isn't bad. Think about what it is that you want to show, right? And then just show it. And again, think about the fact that both of these things are defined in terms of the determinant. So the determinant is probably going to play an important role here, but give that a shot. Think about it. See if you can come up with an answer. I'm only going to give you about 2 or 3 minutes for this one because it's not too bad. Okay, so let's try that 2 or 3 minutes, see if you can knock the answer out there. Okay, so hopefully you managed to give that a shot. There are a couple of ways of actually doing this. One way is nicer than the other. There's kind of like the clever solution, and then there's the more direct one where you just be like, what's the definition of normal? Can we check if that's true? Okay, so let's say, okay, here's our solution. So by definition of normality, it suffices to show, and again, I'm not going to necessarily write this out for every question, but just to, again, emphasize for us, what is normality, right? What is it that we're trying to do? So it suffices to show that if, what do we want to call it? Let's call it M is in GLNR, then M SLNR M inverse is a subset of SLNR, right? And because this is being done for an arbitrary matrix M in GLNR. Okay, so let's I don't know, what do we want to call it? Let's just call it A because we're boring. So let A be an element of SLNR. So M inverse is in MSLNR. And you might get upset here. You might be like, hold on a second, you're doing this backwards. You should have fixed an element in MSLNR, M inverse first. But of course, we know that every such element is represented like this. So I'm going to say that this is okay here. But yeah, strictly speaking, if you wanted to, you'd be like, oh, choose an element in here in MSLNR, M inverse, and let A be an element of SLNR that represents this, right? But whatever, we're not worried about that. And what do we want to do? So we want to show that that's in SLNR, right? But the definition of SLNR is just that it has determinant 1. So let's check the determinant of this thing. Computing the determinant. Gives the determinant MAM inverse, but we know how to work with the determinant, right? So that's the determinant of M, determinant of A, and then we know that the determinant of M inverse is the reciprocal of the determinant of M, right? And here again, it's important that M is an element of GLN, right? So that I can actually, I know that number's not 0. And yeah, what happens? So this thing here, this is equal to 1. And then determinant of M times determinant M inverse, obviously also equal to 1. So yeah, this whole thing is equal to 1. And we're done, right? So thus MAM inverse is an SLNR, which implies that M SLNR, damn it, I keep putting that subscript. If I accidentally do that, you know what I mean, I hope. So it's normal, right? And you can see we didn't need anything about that they were 2x2 matrices or whatever, right? The proof here holds regardless, like so. Okay, and we're done. And again, of course, I wrote out a fair amount here, but really this is a 1 or 2 liner. Are there any questions about that? And also out of curiosity, did anyone do it a different way? Okay. Well, there is another way. Okay, so there is another way, and I'm sorry, I don't remember who asked it or even if they're here today, but somebody asked me in last lecture, like, how do we compute if a group is normal, especially if there's a lot of elements in it, right? So here we have this nice criteria that, we can use the determinant in order to help us out. But I mentioned in the last lecture, one of the key ways that we can do this is we proved last lecture that the kernel of a homomorphism is always normal, right, in the domain. So one way of proving that a group is normal is to show that it is the kernel of a homomorphism. So we could do that here, right? So alternatively, so I'm not going to go through this in full detail, but start thinking about things in this way, because it's a really nice way to think about things. So alternatively, define the determinant map from GLNR into the multiplicative real numbers. Okay, now I can't remember if in the book it's made clear that this is a homomorphism, but this is a homomorphism. Right, and the reason for that is precisely the determinant of AB is the determinant of A times the determinant of B, right? That's precisely the homomorphism condition. So this is a homomorphism. And the kernel of the determinant map, well, those are going to be the set of all matrices, which map to the identity. But the identity of multiplicative R is 1. Well, this is exactly, right, the definition here. I might have to zoom out a little bit. But yeah, this is exactly this, right? So the kernel of this map is SLN and is therefore normal. Done. You like that? I like that one, right? Where you can oh, hey, look, there is, and this wasn't a tricky homomorphism, right? There was a sense in which this was the obvious homomorphism to use. And this is a great way of thinking about things. It really is, or alternatively, what we even could have thought about it. Remember the other day we talked about the preimages of normal subgroups are normal. Well, if we look at the determinant of A being equal to 1, we realize that SLN is precisely the preimage of 1, i.e. it's the preimage of the identity subgroup, and the identity subgroup is always normal. So you could have kind of done it like that as well. So there's all sorts of things that you can do here. If any of you ever go on to take a topology course, topology is a lot of fun. I really recommend it if you ever get a chance to do it. One of the things that you'll realize is it's good to think about things in terms of their preimages, right? If you have a nice function that you can work with and you want to characterize things in terms of their preimages, this is actually a really great way of doing things. And this is an example here as well. Okay. And I think that proof is actually, one, it's slicker, and I think it's even shorter, right? Depending on kind of like whether or not you need to argue this thing is a homomorphism or not, I even could have cut out a couple of lines here, right? And really, I could have made this a one-line thing. So I think that's nice, right? Okay, so let's worry about question 2. So what was question 2? Let's remind ourselves. So we've got this thing, and we want to determine if this is a normal subgroup. So here, of course, we do actually want to play with GL2R. So again, you can assume that this is a subgroup, okay, because it is. It is a subgroup, but the question is whether or not it's a normal subgroup, all right? So let's spend 4 or 5 minutes here, and let's try and do number 2. Okay, so let's determine whether or not this thing is a normal subgroup. Okay, so I'm going to give you 4 or 5 minutes. I'd really recommend too using like Wolfram Alpha or Octave just to make the matrix multiplication a little bit faster. Might make things a little bit easier for you, right? But you know, you do you. Okay, any guesses? Is it normal? Is it not normal? Okay, not normal. So if you want not normal, you just have to give a counterexample. Which matrix did you use? And it was probably a little hard to type it in the chat, right? But because I have a matrix I use, but if you give me a matrix, we'll use yours. Oh, hey, that's exactly the one I used. Yeah, 100%. Let's use that one. All right, yeah, this is exactly what I used. Okay, this is clearly in GL2R, right? Because its determinant is -1, and moreover, it is its own inverse. Right? And I don't know what led you to this one, Hector. The thing that I'm playing with is that I know that this matrix is going to throw, like, it's not going to mess around with A, B, and D, right? It's going to keep them whole, but it's going to kind of throw everything around. In fact, I know it's going to map something into that bottom left-hand corner where there has to be a 0. I know it's going to put something there, right? So my first instinct was, okay, well, maybe the inverse undoes that, maybe not, but I'm pretty sure that this is going to mess things up. So that was kind of my instinct as well. And I chose exactly the same matrix as you, which is pretty cool. And indeed, if we check, right, let's actually just find out. So let's say what do we want to call it? Let's call it matrix M, be A, B, 0, D. So that, okay, let's compute A, M, A inverse. And again, somebody double check me because I am going to do this computation live. And if anyone has ever seen me compute anything, you'll know I am prone to stupid mistakes. So just double check me. Okay. So this will be the second column, BD, and then the first column. Right. So that's exactly what this matrix does, right? It flips the columns, right? It makes the second column the first column and vice versa. And And then, yeah, so now we're going to apply it. So that's what it does if you apply it onto the right. But if we do this last one now here, what are we going to get? So we are going to get D, I think this is going to switch the rows, right? So DB0A, right? So it switches the rows. So when you multiply it on the right, it switches the columns. When you multiply it on the left, it switches the rows. And the net result of that is, yeah, this thing is not in H, right? Because the things in H have to have 0 in their row 2, 1 element, right? It has to be 0 in the bottom left-hand corner. This is definitely not 0 in the bottom left-hand corner, right? If we choose any B, which is not 0, we're going to break this. So this is not normal. So A, H, A inverse is not a subset of H. Thus, H is not normal. Right? Okay, voila, great. Good job. Okay, now we're going to go on to 3. 3 isn't too bad to just do. Like if you just, again, don't, you can just do it, right? Like plug in the definition of normality, see if you can get it. Alternatively, see if you can come up with a kernel example. I think that's kind of interesting. It didn't occur to me to try and do this one with a kernel example. So I'm actually going to try and construct a kernel example right now. But like I said, first run, maybe do it the hard way, see what you can come up with, and then worry about the kernel after. Unless you're a masochist, you want to go straight to the kernel answer by all means. Okay, but it's not too hard to do. And in fact, it is, I think, a pretty nice one to do just in terms of the long way, because it's cool, right? You end up using a couple of different facts here. So let's give that a shot. Again, let's say 5 minutes and see where we go. Okay, so we'll take this one a shot. I think I'd be interested to see if anyone else got it. I think I did find an example where it is the kernel, but I needed next week's material in order to do it. So if somebody has an example where this is the kernel that doesn't require quotient groups, I would love to see it. But I do have one that requires next week's material, unfortunately. At least I'm pretty sure I do. So maybe that's not a great example, at least not until next week, right? So let's do question 3 here. Now, again, what do we know? So we know n is abelian and normal. And n is abelian. Okay, and H is just any other subgroup. Right, we want to show n intersect H is normal in NH. And by stuff that we did last week, we know that NH is a subgroup, right? Right, we proved that last week, or Monday, whenever we met last. Okay, so I like this one. It's kind of a nifty proof. I think this one's really, really cool. And the abelianness actually does come into play here, right? So let's fix an element. So fix some x in n intersect H. And let's fix an element nh in nh, right? So we want to show, again, that if we conjugate x by nh, we get an element of n intersect H back, right? So we want to show that nh x nh inverse is in n intersect H, right? That's the definition of what it would mean for normality. Right? If I can do this for every x and every nh, then we're good. So let's play with this thing and see what we have here. Okay, so if I expand this out, so I've got nh x nh inverse, and that's not a times, right? That's x. So we get n, and then I'm going to rewrite this as h x H inverse n inverse there, right? So I just used the inverse of nh, and we know how to compute that, right? You switch the order, you throw an inverse on both of them. And I've written this very suggestively, right? Because we know that since x is in n intersect H, that in particular, it's also in n, right? So that means that hx H inverse is in H n, or sorry, little h, H n, H inverse, but n is normal. So that means that that's in n. Does everyone agree with that? Right? Okay, cool. Now, in particular, the fact that n is abelian means that, therefore, everything in n commutes. Right? So for this one, here, maybe let me move this line up a little bit just so that I can write beside it. Since n is abelian, so that's equal to hx h inverse, right? But this is now in h. Since x is in n intersect h, which is itself a subset of h, and h is obviously a group, so it's closed, right? And h is a subgroup of G. Okay, so what do we have? So if we look here, we have, oops, sorry, if we look at this, right? So we have, what do we want? So we have NHX, NH inverse is in H, but it's also clearly in N. NHX, NH inverse is in NHN, NH inverse, which is a subset of N. Therefore, it's in both H and N, and so we're done. All right. So NHX, NH inverse is in N intersect H, like so. Okay, did anyone have a kernel example? Like I said, I think I have one, but it's a little bit, it requires quotient groups. And also any questions, right? So if you have any questions, don't hesitate to ask them now. No? Okay, I'm going to assume that everyone's more or less happy with that. That's going to take care of that one. All right, let's do the final one, 4. 4 is a lot of fun as well. I think it's a little bit cleaner than that last one. That last one, you know, okay, what do we need to do? We need to show it's in both N and H. That's a little bit messy. 4 is really, really nice. I really like 4. I think it's a little bit cleaner, but it's the same sort of idea as 3, where you just kind of like write it out and just start applying things that you know and see what happens, right? So I think, yeah, I think 4 is really, really nice. Let's give it a shot. Again, I'm going to give you like 4 or 5 minutes here, and let's see if we can come up with an answer in that time. Okay. So let's take up 4. This one, I am going to, we do need a little bit of a trick here, right? So what do we know? What are we told? I've misplaced the worksheet. Okay, so we're told that H is normal in G, implies, right? What we want to do is we want to show that that means that the centralizer of H is normal in G. And let's recall, right? What is the centralizer? It's the set of things which commute with everything. Right? We're going to need that. That's really important. So it's a collection of elements G in G such that GH equals HG for all H and H, right? So it's the set of elements which commute with everything in H. Okay, so let's just, oh, and here's something we're going to use. And you might be like, well, why are you talking about this now? It's just so that you'll understand what I'm doing when I do it. So xy is equal to yx, right? These two elements commute with each other if and only if x, y x inverse is equal to y, right? Those are the same thing, right? So if you can prove that xy x inverse is equal to y, that's the same thing as saying xy is equal to yx. Okay, so I'm really going to leverage that fact. Okay, so let's actually start doing the solution. And what I want to do is I want to choose an element in CGH, or let's say we want to show. And I really think that for these questions, it really doesn't hurt to write down exactly what it is you want to prove. So we want to show that for every G in G, G, C, G, H, G inverse is contained in CGH, right? Okay, so let's say fix some X in CGH, right? And let's look at and show that GX inverse is in CGH. I think for this question in particular, it can be easy to lose track of what it is that you're trying to show. So it's really worthwhile just to be like, okay, what exactly am I trying to do again? And you spell everything out and you kind of keep track of what it is you're trying to do, right? So you're trying to show GX inverse is in CGH, right? That is for all H in H, we want to show GX G inverse H equals H GX G inverse, right? So we've boiled it down to what it is we want to show, right? I'm not claiming that this is correct, but this is what we want to show. All right, and so that's nice. This is important, right? We've kind of stripped away, and there were a couple of layers to this onion in order to get down to the meat and potatoes of what we actually wanted to do, but we managed to get there. Now, I really want to use this fact, okay? And you'll see why I want to use this. You don't have to, but I think it's a little bit nicer if you use this fact. So what I'm going to do instead is I'm going to look at, so let's look at GXG inverse, or maybe I should say fix some H, right? Because this want to show is for all H. So let's say fix some H in H, and let's look at this thing. Okay, and the reason, H, sorry, that's me being stupid. Now, the reason that I want to do that is precisely because if I write this out, right, like I haven't used the normality of H anywhere, right? That's one of our conditions. We've been given that H is normal, and so far it's not clear where that's going to come up, but I see an H here, and then I see a G and a G inverse around it. I'm like, ooh, that's good, right? I can probably do something with that. So if I expand this out, I get this. Right? And again, I've kind of suggestively, damn it, I used X again, sorry. I've expanded it out, and I very suggestively get this G inverse HG term. And that's phenomenal, right? Because now I can use the fact that H is normal. So because H is normal, this thing is in H, right? Since G inverse HG is equal to H, since H is normal in G, right? So this thing here, you could call it something else if you want. It just depends on how much notation you want, but we know that that thing in brackets is an element of H. And the reason why this is phenomenal is because X therefore commutes with it, right? So X commutes with it. So what this means is that I'm just going to switch it with one of the X's beside it. Like so, right? So here I've used the fact that X is in the centralizer, right? And now we're going to see like a whole bunch of cancellation happens, right? The X inverse cancels, right? These guys cancel. Then this causes the G and the G inverse to cancel. Everything cancels out, and we're just left over with H, right? And we're done, because that's exactly what we wanted to show. right? So we've shown that that is equal to h, and that is exactly this thing in the blue bubble here at the top, right? We showed that x inverse was equal to y. So therefore, I mean, if you really wanted to finish it off, right, you could just multiply g inverse on the other side. Maybe let me write that down in case it's confusing you. G inverse h is equal to h g inverse. And this holds for an arbitrary element h. So g inverse is in the centralizer. And therefore, the centralizer is normal as required, right? Okay, I zoomed out there so that I could put that all into one line. But does that make sense? Are there any questions about that? Because I think, you know, if you're like, well, how would I have known to use that trick in the blue bubble? I think basically, you know, once you write this out, you're like, oh, how do I use the fact that h is normal? Oh, I kind of need a g to show up on the other side of h. You could just put the g there if you want, but there's a natural thing that has a g in it, right? That kind of like wants to be there. So, you know, that's how I constructed this. Again, it's not a guarantee that that's the only way of doing it if you don't want to, but this is what I did, right? I get to here and I say, oh man, I wish there was a g on the other side. Oh, well, why don't we use that? The g that comes from that thing, right? And see if I can make that work for me. And then it does, right? It all falls apart. So that's kind of my thought process when I go through that. Okay, so any questions? Everyone okay with that? Does that make sense? Cool. All right, everyone. Well, that takes care of that worksheet, complete and total done. Yeah, I guess you've all got I guess you guys got a test tomorrow, eh? Anyone freaking out? How you guys feel? Confident? Not freaking out yet. Oh yeah, that sucks. Well, like I said, hopefully it's not too bad. Hopefully it's not too bad. I think you'll all do fine. Like, you are the ones who come to class. So if anyone's going to succeed, I think it's all of you, right? I have confidence in you. Okay. Well, anyway, I'm going to be on Piazza tomorrow. I'm going to keep track of, you know, the questions that come up. So, you know, don't hesitate to ask questions. Obviously, we can't help you, but if there are any clarification that you need, don't hesitate to throw it in Piazza. And by all means, you know, if you're not certain about a question, just ask. The worst case that happens is I just say, I can't answer that, but it's better than losing a mark because you didn't ask, right? So make sure you ask tomorrow. And yeah, otherwise, good luck on the test. Have a good weekend. Yes, yeah, I will be on Piazza today. I have an hour-long break and then I teach 2 more hours though. So I'm not going to be like super on there in the next little bit, but you can throw stuff up and I'll try and answer it, right? Yeah, otherwise, like I said, good luck, good weekend, and I'll see you all on Monday. Thank you. H mod K, those are the left cosets of K, right? So the things that look like this, where G is in H. Yeah, maybe I should write that as like that, where H is in H, right? So they're the left cosets of K, where the thing in front of it can be H. Does that make sense? Yeah, exactly. It's a set of cosets. Yeah. Perfect. It's open book. You'll be fine, right? You can look that stuff up. And in fact, it'll mean something else. It'll effectively mean something else in a week, right? So yeah, you'll be fine. You'll be fine. What's the worst that could happen? Exactly. Yeah, exactly. It's going to mean a quotient, right? But that quotient is going to be also the set of cosets, but endowed with a group structure. So we're kind of like identifying these two things. Let's not worry about it till next week, right? You got a test tomorrow. So All right, I'm going to sign off here, try and grab something before my next lecture. Thanks everyone for coming. Like I say, good luck. I'm certain you'll do well though. Okay, see ya.